All right, so the unit for linear momentum just based on the whatever quantity that's involved. You have kilograms, right? That's for mass. You have v. What is v? Velocity has the unit of meter per second. Okay, so this is a unit for linear momentum. This is when you have a single particle, it's moving with the velocity, then you can calculate linear momentum, which is just mass times velocity. Now, that's you have a collection of particles. Each particle is moving in its direction. And if you're dealing with two dimensions, that particle can move like this direction, that direction, in all directions. So how do you calculate linear momentum of that system? How do you calculate linear momentum of that system? Yes? The speed of central mass, right? Exactly. So when you have a collection of particles, if you want to find linear momentum of the system, we use capital P to indicate that's linear momentum of the system. Then it is equal to the total mass of the system and then times the velocity of central mass. Okay? So this is how we would calculate the total linear momentum. Now, let's see. What is mass times VCOM? Well, we go by definition. Mass of the system times VCOM, that gives you the individual collections of linear momentum, right? Because you have N1V, so let's say your VCOM is equal to MIVI. I'm just going to do this so that it's actually cleaner than that. Okay? So instead of breaking it into the x and y component, I'm just going to express the velocity as a vector. So the central mass of velocity is basically equal to each individual velocity weighted by its own weight. So you have M1, you have MIVI, and then summation of this and divided by the total mass of the system. Okay? So this is that. So when you multiply M on both sides, what do we get? So you have M times VCOM. And then on the right-hand side, you have the collection, the summations of each individual N1, V1, right? So that's how you have N1, V1 plus N2, V2 plus, you can continue depending on how many particles that you have. So you can see that the total mass times the center mass, the velocity of center mass is basically equal to N1 V1 plus N2 V2 plus N3 V3 and so forth. What is N1 times V1? What is N times V? N times V, that gives you momentum. So when you have N1 V1, that gives you P1, right? That's the linear momentum of the particle 1. So you have your P1, and you have N2 V2, that's linear momentum of particle 2, and then so forth. So in other words, and then we identify that this, when you have capital mass times the this, that gives you the total linear momentum. So in other words, to calculate the linear momentum of the system, there are two ways. One is that if you know the mass of the system, if you know the central mass of the velocity, then you just use that equation. Or you can just say, if you have each particle has its own linear momentum, then you just add them together. You find out individual linear momentum, and you add all the linear momentum together. That will give you the total linear momentum of the system, which makes sense as well, right? Because as each individual particle has its own momentum, you add them together. That gives you the total linear momentum of the system. Okay? Any questions so far? All right, so that's C. This is linear momentum, which is mass times velocity. Let's do a time derivative of that to see what we get. So if we do dP over dt, and on the right-hand side, let's say mass does not change. So you have your mass, and then you have your dV over dt. What is dV over dt? That is your acceleration. So you have your m, and then times the acceleration. And what is mass times acceleration? That is a force. What does that mean? It means that the force can be described as the time rate of change of linear momentum. Okay? So, a lot of time you'll hear people saying that Newton's second law. The one that we usually that we're familiar with is that F equals ma. That's Newton's second law. There's another expression for Newton's second law, which is the time rate of change of linear momentum. This is also what we call Newton's second law. Okay? So it depends on whether you're experienced or you just F equals ma. That's a common knowledge, but the time rate of change of linear momentum, that would be someone who already learned physics in order to know that. Okay, so F is time rate of change of linear momentum. So in that case, this is we use this do the time rate of change on applied to a single particle. If you have a system of particle, you can do the same thing here. So you have your d capital P over dt, and on the right hand side, the mass of the system does not change, and then d VCOM dt. And we know that this d VCOM dt, that is just ACOM, right? So that is your ACOM, and so you can see that, and that will be the external force applied to the system. So the force acting on the system is basically equal to the time rate of change of linear momentum. Okay. All right. So if we realize that the force acting on the particle or acting on the system of the particle is the time rate of change of linear momentum, let's look at situations when the net force acting on the particle or acting on the system is 0, and see what we get. So if you apply several forces on the system, but the net force acting on the system somehow to be 0. So what do we get here? So I mean, when I write this force here, implicitly, it means that it's a net force, okay, depending on how many forces acting on a particle. So let's say you have this, and we know. So let's say we have applied force is equal to dp dt. So it's whether it's on single particle or a system, this always applies. Okay, so F equals dp dt. Let's say the net force acting on the particle is 0. When the net force acting on the particle or the system is 0, which means that because F equals the dp dt, this quantity also has to be 0. When you have a quantity, the time rate of change that's equal to 0, what does that mean? It means that this quantity has to be a constant, right? Because it does not change with time. What kind of quantity will not change with time? It has to be a constant. So, in other words, your P here is a constant. So, what does that mean? This is exactly what we, very similar to what we discussed yesterday when you're dealing with energy. Energy within the system, when there's no external force or the net force acting on the system is 0, then energy cannot change. Likewise, when the net force acting on the system is equal to 0, momentum does not change. And the implications of this, when it is a constant, it just means that if you have a system start out with the initial linear momentum, it will have to be equal to the linear momentum after several processes, regardless what kind of processes, as long as the net force acting on the system is 0, then linear momentum cannot change. So again, this equation looks very simple, but the application is a little bit complicated because or can be tricky because you really have to understand the problem to see which part you take it as an initial state, state, and which part you take that as a final state, and during what processes that linear momentum is conserved or not. Okay, so basically very simple physics, but the applications are a little bit tricky, and you can only overcome this overcome this difficulty by doing a lot of problems to gain some sort of understanding about how to apply this equation. So you can see that this is linear momentum, and that just says that linear momentum, so that's one of the important physics laws. Linear momentum is conserved. So this is what we call the conservation of linear momentum. And it is just this. Pi is equal to Pf. And I use a vector form. So which means that, it depends on how many dimensions you're dealing with. If you're dealing with a one-dimensional, great, that's just that. You don't even have to consider. But if you're dealing with two-dimensional, then you have to separate the momentum into the x and y component. So the inner horizontal component, or the initial linear momentum and the final linear momentum has to be equal to each other. Likewise, if you're dealing with two-dimensional, the linear momentum in the vertical and in the beginning, and the linear momentum in the vertical during the final state, they have to be equal to each other. So you can see that they are separated into x and y. You do not say that the initial linear momentum in the horizontal is equal to the final linear momentum in the vertical. It's a big no-no. Okay, you have to separate into the x and the y because they are perpendicular to each other. They don't mix, just like the projectile motion. They are perpendicular to each other. The horizontal and the vertical, they are separated. Okay. All right. Any questions so far? So this is the linear momentum, and so that is that. Let me see. All right. So one of the applications of this that linear momentum is conserved is when you're dealing with collision. Okay. So how do we define collision? Do you play table pool? Do you play pool? Yeah. So tell me, when you play that, how do you play it?
I use geometry.
Use geometry, really?
I try to angle it right.
Yeah. So you have to actually see, at what, so you have basically, if you look at the pool table, is basically like the collision of particles, right? Two particles. So you have the target, and then the one that you're going to, shoot the ball and see, which pocket that you go into. So it does requires a lot of practice, and also look at what angle that when you apply the force, then that ball will go to the designated, slot. So collision is one of the applications of linear momentum, because when you are dealing with collision, it is it's an isolated system, and when you're dealing with an isolated system, linear momentum has to be conserved. Okay, so let's see what is the definition of collision and what are the quantities that are involved. Now, by definition, collision is defined as, in physics terminology, collision is an isolated event in which two or more particles exert relatively strong force on each other for a relatively short time. So you can see that the keywords, after I read out, what are the keywords? Yes. Strong force, short time, right? So time is involved, force is involved, okay, when there's a collision. And we see that, when you have two cars collide to each other, you see there's a lot of force, acting on each other. And the duration of the event is usually very small. So this is the definition of collision, that, you have particles exert forces on one another within a relatively short time. And so when you have, remember, linear momentum is equal to, that's a force, is equal to the time rate of change of linear momentum. So what we can do is that we can multiply dt on both sides. So what we have here is that F, and then now the force is now actually time dependent, because they exert forces on one another within a relatively short time. So that's say the force itself has a time variable. So this is F of t, which indicates that it's a time dependent, and then times dt. And what we have here is that you have your dp here. And what we're going to do is that we're going to integrate on both sides. Again, if you're not quite familiar with that, this is just for your information. Basically, what we're doing here is that we multiply dt on both sides, and we integrate that, so that the time here, so this is integration, from, let's say, initial time to final time. So you have your f of t dt. And then on the right-hand side, you have integration. And that integration, that's say from the initial linear momentum to the final linear momentum. Okay? And so what we have here on the right-hand side, your d, the differentiation, the integration, the sign, they just cancel each other. So what we have here is the change of linear momentum. Because you have the final linear momentum minus initial linear momentum. That just gives you the change of linear momentum. And that's equal to this. What is F? The force dt, and then you integrate that. This quantity, we call that impulse. So we define it as J. Okay, so this is what we call the impulse. So exactly what does that mean? What does impulse do and mean? An impulse is basically the change of linear momentum, and it goes to change the state of the particle. Okay, so the linear momentum is changed if there is an impulse, because impulse is equal to delta p. Okay, this is just for your information. So yeah. So that's the impulse, the definition impulse, and I think what you want to know is that the impulse linear momentum theorem. What is impulse linear momentum theorem? So you can see that involves impulse, involves linear momentum. And just by looking at this equation, we know that impulse is basically the change in linear momentum. That's how they establish each other. So in other words, this is J is equal to delta P. This is what we call the impulse linear momentum. So you have to, if you want to have a change of linear momentum, there must be an impulse involved in order to change the linear momentum. Okay, so that's basically what it means. And you can see that I wrote it in vector form, which means that horizontally has nothing to do vertically. And then you might have an event that that happened only in the horizontal direction and nothing happened in the vertical. And so when you set up equations, those have to be considered. Whether you have to you have the horizontal or vertical vertical collision and stuff. Okay, so now if you look at chapter 9, the last part of chapter 9 is all about collisions. When you have like two balls and then they like to use two particles that collide into each other, it really depends on how those two particles, the motion, they might come head to head, or they move in the same direction, and one is heavier, one is lighter. How the interaction with each other. So in the book, it derived a lot of equations, and I was to say that don't even use those equations because those are too specific. The only equation that you would need is just this. This is very similar to the equations of motion. When they give you a lot of equations, or the projectile motion, they gave you a lot of equations, but those equations are too specific that they are not really useful. What you really need to rely on is this. And this only. Yes. So when in the book it gives you like pages of derivation, the blah blah blah. You know what? It's just based on this. Okay. So don't even bother to copy down those equations, because when you apply those equations, most likely you will get wrong answer because those are too specific. And this is a general form. The only concept that's involved is the conservation in momentum. And I'll just show you a couple examples. Okay, so for example, let's see. Now, before I show you an example, that's to say that collision, there are three different types of collision. And so the collision we basically classify into elastic collision. We also have inelastic collision. And then we have what we call the completely inelastic collision. So when you do problems, you want to know what sort of collision that the particles is is experiencing, because based on different collisions, the criteria and the user equation will be a little bit different. When you have an elastic collision, when we say elastic, it means that no energy is lost. So when you have an elastic collision, it means that kinetic energy is conserved and linear momentum is conserved. So you have two conservation quantity that you can use. In other words, kinetic energy is conserved, so it's very easy. Whatever initial kinetic energy that you have has to be equal to whatever kinetic energy that you end up with. Okay, and momentum is conserved, so you just use Pi equals to Pf. That's conservation of linear momentum. When you have inelastic collision, when we say inelastic, it means that after collision there will be energy lost. Okay, when energy is lost, when you don't know exactly where that energy goes to, or you cannot account for, the only equation that you can use is the only quantity that is conserved is actually linear momentum. So linear momentum is conserved. K is not. Okay, so that's why when you read the problem, you want to make sure, okay, did they specify that it's elastic or inelastic? If they didn't say it is, it didn't say that it is elastic, you cannot assume that it is elastic. Most likely, it will be inelastic. When you have inelastic, you cannot use the conservation conservation energy, to in your equation. The only equation you can use is the conservation linear momentum. When you have a complete inelastic collision, this is the case where you have two balls, two objects collide into each other and they stick together. When they stick together, this is what we call the complete inelastic. Okay, so when they complete, we know that that's inelastic, which means that energy is not conserved. In addition to that, because they stick together, now the total mass will become the mass of the summation of those masses. So it's the mass of the system, not mass of each individual particle. So P is conserved. K is not. Okay, so you can see that conservation of energy is very, it's not always applied to every situation. It really depends on what kind of collision. But just based on this, you can see that momentum is always conserved, regardless whether it's elastic or inelastic. So whenever you do problems, the first thought that comes to your mind is that this, okay, identify that this is a collision problem. If it's a collision, then momentum has to be conserved, regardless whether it's collision whether it's elastic or inelastic, so long as you're dealing with an isolated system. Now, in physics 311, you're dealing with the most of the time it's the ideal case. So a lot of time, not a lot of time, for all times in physics 311, you'll be dealing with isolated system. So you can just use that conservation linear momentum, and you won't do wrong. Okay. All right. Any questions so far? All right. So as I mentioned, the book has a lot of equations. When it comes to collision, and really, they are not that useful. So let me just show you a couple examples. Let's say when you have a particle, so let's say horizontally. So now we're just doing horizontally. You have a particle. Let's say you have two particles. So this is your M1. This is your M2. And let's say this is moving with the initial velocity. So that's v1 and initial velocity. So now instead of just one subscript, whenever you're dealing with collision, the symbol can be a little bit massive. But then that's how you keep track of which one is which. You should use two places for your index. Okay, so you have v1. One is for particle 1. I indicate that's initial. Okay, so this particle is moving rightward with the initial velocity v1I, and this particle, let's just say in general case, it is v2 and I. Okay, now we can set it equal to 0, later. So let's say you have two particles in the beginning. They're all moving with a non-zero velocity, moving rightward, and this particle is actually moving faster, so it's going to collide with that particle. So that's after collision. So this is before. And then I say after collision, this N1 move in this direction. Let's say V1F. And this particle, let's say, is moving in that direction. But then its velocity changes, so that's called a V2F. So you can see that. So this is before collision, and this is after collision. You can see that you really have to use two subscript. One is for which particle, and the other one is indicate whether it's initial or after collision. So let's say in this case you have two particles. They all moving rightward. One, before collision and after collision. Particle 1 moves leftward, and particle 2 continues its track moving rightward, but it changes velocity. And likewise, particle 1 also changes velocity as well. And let's say if, so how do we calculate, how do we set out the equation? Which quantity is conserved? Huh? Linear momentum is conserved, right? So in this case, because we're dealing with one-dimensional, so it's very easy. So you can, and I did not mention whether it's elastic or inelastic, so you can't use the conservation of energy. You will have to use conservation of linear momentum. So let's say, how do we set up, based on the conservation of linear momentum, how do we set our equations? So you would say linear momentum is equal to final linear momentum. That's your starting point. And because you're dealing with one-dimensional, so you can just say that Pi is equal to Pf. So now we just have to figure out what goes into Pi, what goes into Pf. Pi indicates linear momentum before collision. So let's look at the picture before collision. How many turns are there before collision? There are 2 turns, right? This one is moving with the velocity. This one is moving with the velocity. So there are 2 terms. Each will contribute to linear momentum. So how would you write it? You would say N1 V1 I, right? The symbol is very important because that's how you keep track of each quantity. So N1 V1 I plus N2 V2I, that's your linear, okay? Before collision, that's the only 2 terms. All right, and it has to be equal to the final linear momentum. So how would you write the final linear momentum? N1, huh? V1F, and then, is that right? Plus, is that right? Why is it negative? Exactly. It is leftward. So we have to put a negative sign because it's leftward. Huh? Yes?
Well, since velocity is a vector and it has its own value as a negative vector, should you just be adding it up and then once you add
No, you would say that N1 V1 I. If you will do that, then you don't have to put that. But then I'm using the magnitude, so I have to actually put a negative sign. If you just express that in vectors, so that's if you express that in vector, this is how you will write it. So N1 V1F plus N2 V2F. In vectors, that's fine. But then when you're using the magnitude, because we're dealing one-dimensional, so I just use a magnitude, then you have to put a negative sign. And then with the understanding that your V1F is a positive value. Okay? Yeah, okay. And then so you have your M2 V2F. Okay? So this is how you set up the equation. As you can see, the symbols are very important. Okay? You have to use, instead of just 1, you have to I and F, because otherwise you'll get confused. Okay? So this is the case when you have that. And so that's in this case, so in the book, he also utilized this, but then he would say, okay, what if this is 0? If this is stationary, if you have a stationary target, which means that this goes away, okay? So when you have a stationary target, let's say your V2I is 0, and then you would just say that the only term in the beginning will just be N1 V1I, and the rest stays the same. Okay? Or in the book, it also said that, if you have a massive target and then blah, 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 all that stuff, really it just get a little bit confusing and really not useful. So the only equation that you would use is just this. And based on, and then what is the expression for P? That just MV. Then just use that and see how many turn that goes into the contribution to the total momentum of the case, and then set the equations like this. That would be my suggestion and recommendation. Instead of copy down all the equations, write out that it's really useless, to be honest. Okay, so this is one-dimensional case. Now let's look at a more realistic case when let's say you go to the bar, you're playing the pool, and then you want to show off your skill that you learn your math, you learn your physics. Okay, show them how to apply the conservation of momentum. Let's see how to do that. Okay, so this is one-dimensional case, and you can see that the direction you have to take that into account. If it's leftward, it has to be negative. If it's rightward, then it's positive. So let's say you have a target. So this is the XY. Let's say this is your M2, stationary. Okay. And I'm going to, let's see. By the way, in the lecture notes, I don't know which page, but there's a, it should be expressed, the moving target, because the diagram is actually, you have two balls colliding into each other. You really have to, you really have to express that in vector form instead of using the magnitude. Let's see. All right, so this is your M2. That's so you have M1. That's moving rightwards. So this is your M1, and it's moving at the velocity, let's say V1I. I'm going to express that in vector form because now we're dealing with two-dimensional. So now this ball is collide with, and your M2 has initial velocity. We call that V2I is 0. Okay, stationary. So this ball is going to come in contact with this, and it's going to collide with the M2. And after collision, so before collision, this is before collision. After collision, this ball moves to this angle. Okay, and acquire a velocity. So this is your M2, and then with a velocity, we call that V2F. Okay, and then your M1 after collision is going to move in this direction. So this is your M1. And this is your V1F. All right, so in this case, you can see that you have one ball in collision with the second ball. And the second ball is moving up, and the first ball is moving down. And the angle, that's called this. The one with the mass 1, that's called a theta 1. The one with mass 2, that's called a theta 2. All right. So, in order to relate all this velocity together, where do we start? And again, I did not mention whether it's elastic or inelastic, so we can't just use the conservation of the energy to set up equations. Yes?
I'm assuming theta 2 and theta 1 are different?
Yeah. That's why I use theta 1, theta 2. It might be, they might be the same. We don't know. So in that case, how do we apply conservation linear momentum? This is two-dimensional, so you should have two equations, one for the horizontal and one for the vertical. Okay. Now, let's say VI is equal to VF. So let's start with the horizontal component first. All right. So you will have PIX, that's equal to PFX. This indicate the linear momentum in the horizontal direction. This indicates initially, and this is the final linear momentum in the horizontal direction. They have to be equal to each other. How many turns that will contribute to the linear momentum in the horizontal direction? You have one that's stationary and one that's moving rightwards. How many turns will there be in the horizontal initially? 2. What are the 2? Okay, N1, V1, I, right? Hold on. And then you have your N2, V2I, right? Okay? And then, but then this is equal to 0 because it is not moving. Okay? So the only term that will contribute to initial needed momentum would just be N1 V1I. Okay? Because I used this V1I and just rightward. Okay. Now, final needed momentum after collision. How would you find, how many turns are there? 2. What are the 2?
Negative
Okay, negative N1
V1
V1F. And then?
plus
This is particle 2, particle 1 that's moving in that direction. And the velocity is in that direction, right? So velocity is a vector. It's not along the horizontal direction anymore. We're finding needed momentum in the horizontal direction. So this will be, you have to resolve your velocity into the x and y component, right? And only the x component will go into this equation. So in that case, that will be cosine theta 1, right? So because your V1F, you have to resolve this vector into the x and y component. So the x component is this. So that's your V1F and then cosine theta 1. And it's negative because it's pointing, oh, is it negative? It's positive, right? So you have N1 V1F and then cosine theta 1 horizontally. Right? Horizontally, it is rightward, so it is positive. This is coming from particle 1. All right, now, what about particle 2? M2, V2, F, cosine theta 2, positive or negative? Positive, because your V2 is moving in that direction, so it has a positive x component, right? Do we have any other terms? No, okay, so you can see that before, only particle 1 will make contribution to the needed momentum in the horizontal direction. After collision, you have 2 terms. You have one that's coming from the particle 1, one that's coming from particle 2. And you have to resolve the velocity into the x and y component and just use the x component in this case. Okay? Yes?
Why is it positive and not negative since it's going downward?
It is going down, but again, this is two-dimensional. Horizontally, positive or negative?
Positive.
Yeah,
Oh, so
we're
that's
doing positive, right?
Oh, okay.
Vertically, it is negative.
Okay.
Okay? So, all right, good. Now, you can see that most of the time, that equation will not be useful, will not be good enough, will not be useful enough. You have to rely on an additional equation. That additional equation comes from the consideration of needed momentum is conserved in the vertical direction. So you have the P1, PIY is equal to PFY. The needed momentum in the beginning and the final, they have to be equal to each other. Now, what's on the left-hand side? What is the needed momentum in the vertical? Good. It is 0 because there's no vertical motion, so it's 0. On the right-hand side, what will be the first? What will be? How many turns are there? 2. What are the 2? Let's start with the M1. Negative M1. Sine theta 1, exactly, because it's pointing downwards, right? And then so you have negative M1 V1F sine theta 1, and then what's the next term? Sine theta 2, right? Okay, so you have this equation and this equation, then you can solve for whatever you ask, fine. Wow. It's not that complicated, right? Exactly. It's just that the symbol is a little bit messy because there's just too many. So it's like 2 particles, initial and before, so now it's like 4 parameters, before and after particle 1 and particle 2. So that's why you want to make sure that you keep track of the symbols. That way it's make your life easier so you know which one you're dealing with. And needed momentum, again, these are vectors, so you have to resolve the vector into the x and y, and then resolve it. On the x component will go into this equation, on the y component will go into that equation. Okay. Now, if the problem says that the collision is elastic, you can also have an additional equation to you. That is the conservation of, conservation of energy. So let's say if this is elastic, how would you write the equation for the conservation of energy? We know that for elastic, Ki is equal to Kf. So how would you set up the equation? Initially, this is moving. This does not move. So this has no kinetic energy. This one has kinetic energy. And what is that kinetic energy? M1 V1I squared. That's your needed momentum. That's your initial kinetic energy, right? Final kinetic energy. How would you write the final kinetic energy? How many terms are there? 2, because both particles are moving. So give me the first one, the particle 1. And 1. V1 final square. Great. This is how when the energy is conserved. This is after collision. You have 1 half m1 v1 f squared plus 1 half m2 v2 f squared. You can see that when I calculate the energy, I'm using this, right? v1f and v2f. I did not use v1f cosine theta. I did not use v1f sine theta. You do not have to resolve this vector when you calculate energy because energy is a scalar. You do not treat it as a vector. So in other words, the velocity that goes into calculation has to be the total velocity, whatever velocity that's given. Okay, these are components. They do not come into the calculation of energy. It is this quantity that goes into calculation of the energy. All right? Okay? Any questions so far? So, I want to do another example. When you have a completely inelastic collision. So, let's say you have two particles before collision. So, let's say two particles, M1, M2, let's say, now I'm just doing the one-dimensional. So it's V1, V1I, you have V2I. So this is before. After collision, they stick together. Okay, and they're moving at the same velocity. How would you express that velocity in terms of V1I and V2I? And that's it because they stick together. The total mass of the system is just capital M, which is M1 plus M2. So before and after, before they're each moving at the velocity, after collision they move together, so they have to have the same velocity, and the mass is the combined mass. So how do we do that? So again, this has to be equal to this. I'm dropping the x because it's a horizontal direction, so we don't have to consider vertical. So now, what will be initial? Initial, that will be M1 V1I plus M2 V2I. That's your initial needed momentum, right? After collision, what would that be? What is your needed momentum after collision? Where does that M1 and M2? Yeah, okay, so you can say that it's M1 plus M2. So that's your total mass. This is your capital M. And then what? Huh? That will be just V, right? Because I already defined that to be V. Okay, so this is how you set the equation when you have a complete inelastic collision. You sum up initial needed momentum, and then after collision, because they stick together, mass become the combined mass. Velocity, they move at the same velocity. So you just use a 1 v to indicate that's velocity. And then you can find out, depends on what quantities you're given and stuff. Okay? All right, are we good? So this chapter also deal with the the rocket, which is a little bit complicated. So I'm not going to go over that. So as long as you you know the definition of center of mass, linear momentum, the implications of linear conservation linear momentum, that will be good enough.